So hello everyone, my name is Pritam Paul and welcome to another video of the tree playlist. If you haven't watched the previous videos, I would like to advise you to go through the previous videos first, learn about tree and then come to this video. And if you know about all those things and if you want to start from binarysearch, you are most welcome. Okay. And by the way, the lecture notes, like all the handwritten notes which I'm going to write here, that would be in a drive and the link would be in the description. Don't worry, you just download that PDF and enjoy. Okay, so today's topic is very important because today we are going to talk about binary search tree. Okay, this is one of the most important data structures, one of the most important data structures in your career. You will be using it every single where in product development, building websites or building anything. Like binary search tree concept is going to be used almost everywhere, you will find. Okay, so what is binary search tree? The name, the purpose is in the name itself. It is efficient in searching elements. So one of the most important uses of binary trees is in searching. So binary search trees are those binary trees that are specially organized for the purpose of searching. An element can be searched in over O of log n time complexity, whereas in array it is O of n, in linked list it is O of n, in stack it is O of n, in queue it is O of n, everywhere is O of n. The worst case scenario, best case obviously O of 1. Okay, in average case and worst case it is O of n. Okay, but in case of binary search trees, in every, like in worst case or in best case or in like everywhere, best case obviously O of 1, like the average case and the worst case would be O of log n. Okay, so obviously using binary search tree, if the time complexity is O of log n, that means it is very efficient in searching. Okay, a binary search tree is a binary tree that may be empty. Yeah, maybe empty. If it is not empty, then it satisfies the like few properties. Now the first property would be, okay, all the elements of left subtree would be lesser than root. All the elements of right subtree will be greater than root, and obviously left subtree and right subtree would be what? Would be binary search trees. Like they also need to satisfy these two. That's it. Okay. Now for example, if this is a 10, 11 and 12. So here 10 is not greater than 11. Okay, the root is not greater than the left element. Okay, that's why the first condition would be false. That means this is not a binary tree, sorry, binary search tree, not a BST, correct? But if I am having this, that means obviously the root is obviously greater than left element and the right element is greater than root. That means obviously it is a binary search tree, BST, correct? So this is a basic example. We have assumed that all the keys of binary search tree are distinct. It has to be. Okay, we can't have duplicate elements in a binary search tree. Okay, normally we can't have duplicate elements in a binary search tree, although there can be binary search tree with duplicates. Normally we can't have. Okay, but we can use. At that time the code has to be changed, code has to be an updated one for that favorable cases. Okay, now for now, like all the operations, we are considering that we can't have duplicate elements. Okay, and accordingly we are heading on. Okay, let's give some example and you will understand like how the things are. For example, one tree could be 22, then 15, and then 45. Now here in the left subtree, it could be less than 15, but here it has to be greater than 15 but less than 22. So let's take some example which is 10 and 20. Here it has to be greater than 22 but less than 45. Let's take 30. And here it could be like anything, for example 80. So this is a binary search tree. Binary search tree. Why? Because obviously first condition is satisfying, second condition is also satisfying, third condition is also satisfying. Third condition is what? Third condition was like this left subtree and right subtree also needs to be BST. Otherwise, like this is a recursive thing, right? Otherwise it won't be implemented properly. Okay. Another example could be like this. For example, 67, then 34, then for example 12, for example 45, for example it should be 38, and it should be for example 50. Okay. And here it could be 80, and it could be 78, and it could be 95. So this is also a binary search tree. This is also a binary search tree. Okay, these are the examples actually. Like another binary search tree could be like this. For example 50, 70, for example 60, then 65. This is a skew tree. You remember, right? Skew tree. But also this is a binary search tree. Okay, for the obvious reasons. Now another example could be like this. For example, it is 10, 15, 20, 25, 30. This is also a skew tree. Yeah, but also a binary search tree, because all the elements are in the ascending order here. Yeah, the reverse also could be there. For example, it could be 50, then 40, then 30, 20, and then 10. So here all the elements are in the decreasing order. So it is also a binary search tree. We can see it's a skew as well, it's a BST as well. Okay, so these are the examples. Now let's go to the traversal of a binary search tree. So let's take an example. So this is a binary search tree, and let's implement the prefix first. So prefix could be like 67, then 34, then 12, then 10, then 45, 38, 60, 80, 78, 95, 86. Then postfix. Postfix. Then postfix could be like 10, 12, 38, 60, 45, 34, 78, 86, 95, 80, and 67. But when I call, so, no, sorry, it's not post prefix and postfix. I'm really sorry. It's pre-order, pre-order traversal, and post-order traversal. We are talking about traversals actually. I'm really sorry. Now it's in-order traversal. So now the in-order traversal would be like 10, 12, then 34, 38, 45, 60, 67, 78, 80, 86, and 95. Yeah, so if you see the numbers would be in ascending order. Like in pre-order and post-order, things are normal, just like binary tree. But when it's come to binary search tree, you need to remember that the in order traversal of the binary search tree, all the numbers, if the nodes are having integers, all the integers would be in ascending order. This is a universal truth. Okay, this is a speciality of in order traversal of the binary search tree. Okay, now searching in a binary search tree, how would we search? Now I am discussing about the uh, theory. Like I am not going to the coding part, we will talk about it later for sure. Okay, now for example, now let's talk about this one, the searching in a bst. How would we search? What is the algorithm? So let's go to that example again. 67, 34, 12. So this is a binary search tree. Now here we need to search 45. Okay, so first one would be, we would be comparing 45 with the root. Okay, so 45 is greater than 67 or not? 67 is greater than 45, isn't it? That's why we would be going into this direction, that means in the left subtree. As 45 is less than 67, then obviously it has to be in the left subtree. That's why we moved into the left subtree. Now we have to compare like 34. So 34 is less than 45. That means the 45 might be, okay, the 45 might be, if it is not there in the list, that is another. So that's why I'm saying might be in this tree, in this subtree, correct? That's why we are going to hit this one. Okay, now the cursor is here and we have to check like 45 is equal 45 or not. Okay, as the search is 45, if it is equal, then obviously found. Okay, and if it is not, then obviously, for example, if it would be 48, then what would go? Obviously you will go into this side and it will check, then 60, nothing, then obviously not found, right? Like in this way we have to think. So in this way we can implement the searching operation in a binary search tree. Okay, now finding the finding the nodes with minimum and maximum key. Okay, so this is a very common thing. Like for example, the minimum value is here, the maximum value is here. You need to understand one thing, the leftmost element of the tree, leftmost element of a BST would be the minimum one, and the rightmost would be the like max. This is a simple method, we will do the coding part later. Okay, I'm just giving some examples. Now what about the insertion in a binary search tree? How do you insert data? Searching we got to know, and there are another method which is array method. Like we will talk about it later when the binary search algorithm we will talk about. Okay, for now just binary search tree you need to know, that's why I am discussing all these things. Now let's talk about the insertion. Okay, now let's take an example. Okay, for example, 67, 34, 12, 45, 38, 60, 80, 78 and 95. Okay, now you want to insert what? Insert 39. Okay, So if you want to insert 39, then obviously what will happen? The 39 have to compare. It has to compare with 67. So 67 is greater than 39. That means 39 needs to be in the left subtree, isn't it? Then obviously the cursor will go here. You have to check 34 is greater than 39. Then obviously this part would be there. Okay, so the cursor will come here. 45 is greater than 39, obviously. Then it is coming here. Now 38 is greater than, sorry, 38 it less than 39. That means 39 is greater than 38. That means this part would be added here. In this way we can insert. The time complexity of insertion would be O of h. H is the height of the tree. Why height? 1 2 3 4, like all the levels we are going through, right? So in this way. Okay, now if you want to insert 90, then what will happen? Then obviously cursor will check here. 67 is sorry, 67 is less than 90. Then it will come here. It will check 80 less than 90. Then obviously it will come here. Now 95 is greater than 90. That means it is going to come here and add 90. That's it. In this way we can add data. By the way, this O of h could be written as O of log n. Why log n? Because h could be replaced as log n, right? Isn't it? So the deletion operation now. Deletion in binary search tree. There are three cases which needs to be handled. Okay. The first one is node has no child. Okay. So obviously it has no child, that is it's a leaf node. Node has exactly one child and node has exactly two children. Now we need to understand. For example, the case 1. For example, 67, 34, 20, and then 80, 78, 85. Now if you want to delete this one, you can directly delete it because it is a leaf node. If you want to delete it, you can directly delete it. Obviously it is a leaf node. It is also a leaf node. You can directly delete it. Okay, but so for example this is getting deleted. Then obviously what will happen? 67, 34, 80, 78, 85. That's it. Okay, now let's talk about the exactly one child. Case 1, sorry, case 2. Okay, case 2 में क्या होगा? For example 67, 34, 12, 45, 82, 78. Okay, now if you want to delete this one, then what will happen? This will come here and will take the responsibility. That means the resultant would be 37, sorry, 67, 34, 12, 45, then 78. That's it. This is the case 2. Now the case 3. For example 67, 34, 40, 20, 81, 78, 95, 89, 98. Okay, so now if I want to delete this one, this 81 I want to delete. Okay, now what will happen? Like here there are two subtrees, first one, second one. Who will take the thing? So here a concept comes which is called in order successor, which is in order successor. Okay, so if I like make the in order traversal. Okay, what will happen? 20, 34, 40, 67, 78, 81, 89, 95, and 98. So the like after 81, what is the value? 89. So this is the in order successor actually. In order successor means in order traversal, the next element of that node would be the in order successor. That means 89. So this 89 is going to be put here and this would be deleted. Okay, let's see. So in this way the deletion also happens. I'm giving you some examples, that's it. Okay, I'm not going into the coding part, that's why I'm covering all the things in a single video. We will talk about it later obviously. So this is all about the binary search trees. I have talked about the deletion, case 1, case 2 and case 3 both, and then insertion also, like what is the time complexity, obviously log n, what is binary search tree, actually searching in binary search tree, and what is a binary like such tree, actually traversal and all, every single thing I have discussed for the theoretical concepts, what is exactly trees are. Okay, so this much for today, and see you in the next video obviously, and we will talk about more on binary search tree. So this much for today, and subscribe the channel guys. You guys watch the videos but don't subscribe. Please try to share the video also with your friends who really wants to be have a stronger concepts in data structures. He or she, just share with them. Thank you so much and see you in the next video.